of Calculus 3, and in this part we are moving to triple integrals in cylindrical coordinates and spherical coordinates. It's a topic in section 5.5. How about first let's look at cylindrical coordinates. So this is this chart here. It is just for quick reviewing purpose of cylindrical coordinates. Instead of the rectangular coordinates x, y, and z, we are using the order of the triple r, theta, and z. R, theta, really, they are directly from polar coordinates. So I really don't have a lot to provide about the cylindrical coordinates. It is a very straightforward extension from polar coordinates, and the z stays the same, the so-called cylindrical coordinates. And also it might be very helpful to review some surfaces in the three-dimensional space for both rectangular and cylindrical coordinates. X squared plus y squared equals c squared. Okay, in the three-dimensional space, do not just take this as a circle. It is a cylinder, circular cylinder, okay. It represents all the circles stacked around the axis from top to bottom. This circular cylinder. And then another graph, it is z squared equals the c squared, let's say just 1 to make the discussion easy, okay. Z squared equals x squared plus y squared, and clearly it's not a sphere. And to understand that clearly, it is a circular cone. And because of polar coordinates, x squared plus y squared equals r squared. So using the cylindrical coordinates, we get z as c times r. And for the cylinder, previously we discussed, it simply can be represented using cylindrical coordinates as r equals c. And also when you have a sphere, the surface x squared plus y squared equals z squared, that's a sphere, right? And if we insist with cylindrical coordinates, because x squared plus y squared equals r squared, so we simply have the equation like this. And also it's worth to mention, usually when you have spheres involved, we are going to use spherical coordinates. Okay, it's just a lot easier. Also, it's, well, you can tell from the name-wise, spherical coordinates, they are used to deal with spheres. And the cylindrical coordinates, they are used to dealing with circular cylinders. Actually, it's right here. And for the paraboloid, this is the surface of paraboloid, and I hope you understand. Indeed, there are circles involved. If we look at the projection into the xy plane, they are all circles. Or these are the so-called contour map or level curve. They are all circles. Okay, so I suppose for now we should be familiar with those equations and surfaces. And then we are working with a triple integral, right? The bigger question is, how do we evaluate a triple integral using cylindrical coordinates? I say somewhat it's relatively simple, and still you are going to know the result for polar coordinates, okay? This is how we write a triple integral in general. And then using polar coordinates, you want to change everything into r, theta, and z. So x is replaced with r times cosine theta, y is replaced with r sine theta, z stays the same. And don't forget, this part, basically dv, it has dx, dy, dz. dz stays because z coordinate is unchanged. Then dx, dy, it is for the area, right? And then did we say when we use polar coordinates, you're going to use r, dr, d theta to replace dA or dx, dy, dx, those things. So indeed, for cylindrical coordinates, you do have the actual r2, r, dr, d theta. That is really directly from polar coordinates, then times dz, times dz. This is the so-called forbidden theorem in cylindrical coordinates. Cylindrical coordinates. Okay, and then let's take a quick look how we use the cylindrical coordinates to solve some problems. And this time, what we are considering here is we are considering a region bounded below by the cone. Z equals square root. We just said actually we do have the cone surface right here. Z squared. If you take a square root of both sides, so Z tends to be square root of x squared plus y squared. Okay. And the paraboloid is Z equals 2 minus x squared minus y squared. If you take a look, this is the paraboloid we just mentioned. Z equals x squared plus y squared. And then we have negative x squared, negative y squared, which means we are going to have the paraboloid upside down, moving downward, pointing downward. Okay, and then add by 2. This is the meaning of 2 here. Add everything on the paraboloid surface by 2, which really means the entire surface, it is being moved 2 units upward. Starting from the vertex 2, everything points downward. Okay. And we want to see how we can evaluate the volume of the solid bounded by the region. Find the volume of the region. Okay, find the volume of the solid. And I think I don't need this part. Mostly this is the example from the textbook, but anyway, I really did not exactly the same thing as on the textbook. The textbook did not evaluate, and also I think the textbook did a little more things. But anyway, for our class purpose, simply it's not required. So if you have any doubt how the surface would look like, this is how the solid or region would look like. We do have the paraboloid opening downward. And then this is the cone surface, circular cone opening upward. So they do intersect, right? And the volume we are talking about here, it is the lower part bounded by the cone. The upper part, it is the surface, the paraboloid. Okay. So first, what I did here is I tried to find out the intersection of the cone and the paraboloid, the circle, right? What kind of circle is this? So this is my calculation. Z equals the square root, and again because of the cylindrical coordinates, x squared plus y squared equals r. And again because x squared plus y squared equals r, the second surface, this is the paraboloid, the surface on the top, also can be converted into the fashion of r, And then those two surfaces intersect, which means they have the same z value. So I put those two equations together, and it tends to be a quadratic equation, and it can be factored. R equals 1, and certainly if you insist, you say R could be negative 2, could be, but anyway, we consider R as a distance, so R is not negative at all. We are only having R equals 1 as the solution of the intersected equation. R, it is a radius. R equals 1 in the xy plane simply means the R equals 1 in a particular plane, it simply means it's a circle. And also because z is square root of x squared plus y squared, because r, it is 1. So I'm saying the intersection, it is circle of radius 1. It is in the plane z equals 1. And then finally, this is what I figured out. Okay, the description for this solid here, what we are having here, using cylindrical coordinates. And the r is changing from 0 to 1. Theta, it is, we do have the entire circle here, right? So theta is changing from 0 to 2 pi. And then z, it is moving from the lower surface, which is 2 minus r squared, to the upper surface, upper surface, which really it is, this is actually, this is the lower surface, z equals r, and this portion, this it is the upper surface, z equals 2 minus r squared. So accordingly, using cylindrical coordinates, I figured out the triple integral should be evaluated into this fashion. And also another thing I just realized, I should have mentioned this earlier. Another way to explain a triple integral, if you set the integrand equals 1, and then the triple integral can be considered as volume. So this is exactly what I did. Triple integral over a solid, and then the solid, it is represented using cylindrical coordinates. So we do have r dz dr d theta. And r as z, as we already explained somewhat, it is observed from the graph. Okay, this lower portion, it is from a cone, so that's r. The upper portion, it is from the paraboloid, so that's 2 minus r squared in the integral. Okay, and also don't forget that there's actual r there, r dr. And then dz, z is moving from here, right? From here. And then r, it is changing from 0 to 1, 0 to 1. Theta, it is changing from 0 to 2 pi. And then we finish the evaluation. Hopefully, well, you help me double check with the number. For now, I think it looks fine to me. And if you see anything not right, just let me know. Thank you for watching.